All right, yeah. Hi, everyone. I'm Alex. I'm an undergraduate at UC Berkeley, working with research IT. And let's jump right into it, starting with our first slide, which is basically the thesis of this presentation. Sometimes this doesn't cut it. This being your personal laptop or workstation or computer that you're probably currently watching this Zoom on. And a lot of researchers are using their personal computers for research, but it doesn't always fit. As research grows more computationally expensive and as data sets get larger and larger, sometimes stretching into the terabytes or petabytes, just enormous amounts of information that need to be processed, computational resources need to grow as well. And so, slide. Today, we're going to show you some ways you can expand your computational horizons. We're going to start with why you might want to consider using remote or high performance computing, and then go into some strategies for using that, such as parallelization, the cloud, containers, virtual machines, all of these fun words that we're going to explain. And then we'll give you some computational resources that you can go out and look for at your institutions or nationwide, many of which are free to get started. Slide. So let's just get started by defining some key terms that we'll be using throughout the presentation, explaining more later on. Starting with remote computing resources. So you can think of remote computing resources as anything that's not your computer sitting right in front of you. From computers that are remotely accessible to giant clusters of thousands of servers that work together to run code. High performance computing is a subset of remote computing that focuses on high performance. So that's having a lot of storage, a lot of memory, just a lot of computational power that isn't really accessible on a computer you can have in your house. And then RAM, CPU, GPU, storage, these are all important resources that computers offer that allow you to do work on computers. So RAM is basically the memory that a computer has that's instantly accessible, that the computer can run computations against using a CPU or a GPU. A CPU basically does the computations on a computer. A GPU is a more specialized CPU meant for graphics or other specialized work. And then storage is where long-term data goes and is usually, lets you put more data than the rapid access memory, RAM. Next slide. So let's just go through a comparison of your laptop or workstation versus remote computing resources. So if you're running some code on your laptop, trying to do research, you might have to run that code overnight because your data set is so large, your code is relatively slow because you don't have the computational resources you need. You could run out of memory because 16 gigabytes of RAM may not be enough for your data, which throws errors and sets you back. You have to hope you have enough disk space as data sets grow increasingly large. The terabyte of storage on your laptop just may not be enough anymore. And finally, you have to hope that your computational requirements don't increase in the future. As research workflows grow increasingly intense, if you don't adopt high performance or remote computing workflows, then you could be left in the dust as your laptop no longer works for your research. In contrast, remote computing resources are available and accessible. You can get on them 24/7 and run code whenever you want. You don't have to actively monitor them or cross your fingers that a last-minute Windows update shuts down your research because they're always there. They're highly scalable, so you get as many resources as you need and access to the latest hardware, including expensive GPUs that you often just can't get for your workstation. Slide. So here's the bottom line of how these systems work generally. You ask for resources and the system provisions them. This allows for far more scale. For instance, the system I and my colleagues work on, called Savio, UC Berkeley's supercomputing cluster, has 3 petabytes of storage. Your laptop has about a terabyte, which is, again, 3,000 times more information, more data that can be stored. and you can have a piece of that for your research and your data sets. Sabio can perform 500 teraflops of computations, just a measure of how fast a computer is. Your laptop, 50 gigaflops. Again, thousands or tens of thousands of times more powerful. Slide. So here's a diagram of roughly how our system works. And every system is going to be different, but this just provides a good model for what we're looking at on the inside. Basically, you go on your laptop and use something called SSH to get into one of our login computers. This connects you to the entire system, where you can access and upload your data and run code against our many servers, which are called compute nodes. They're all connected through ultra-fast networking to our massive file storage system, which allows you to work against locally stored data of basically any size. And when you run code, you can request to have more compute resources if you need them. So you're not just limited to one computer, but you can use strategies that take advantage of dozens or even hundreds of computers. Slide. Here's a case study of what switching to high performance computing might look like. So the case study here is a researcher who's working on weather simulations to study conflict in East Africa. They're running the simulations in R, which isn't necessarily the fastest language, but it's what the workflow is written in. And it takes a long time to run on their Mac, about 36 hours. There's also problems with memory overflow, since when a data set gets very large and R likes to hold it in RAM, this can cause errors. So when the researcher switched to high performance computing, they could still use the same code, but they could apply certain optimizations to take advantage of having a more powerful computer, or just leave it as is and let it run without having to worry about keeping their laptop on for 2 days. You can also use a machine with larger memory and more storage to get rid of those concerns about memory overflow. Slide. So here's what it comes down to. Remote computing offers new ways to collaborate. As research becomes increasingly computational and increasingly global, it gets difficult to share all of your data and results with collaborators who might be on the other side of the world. But remote computing lets you put all of your research in one place. Everyone's running code on the same machine. All the data is in the same place. So you don't need to go through like complicated transfer strategies to get the data to where it needs to be. And all of your results are also there. So everything is in one system. Slide. That's why so many researchers are adopting high performance in remote computing. I mean, this is just a partial list of some of the fields we've had come in over the past few months for consultations: biology, public health, environmental science, economics, chemistry, and so many more. Researchers in virtually every field are adopting these strategies to go beyond their personal machines and take advantage of modern advances in computing technology. Slide. And so that's why we're doing this presentation. And I just want to give you a few things to keep in mind as you watch the rest of this workshop. The first thing you need to ask yourself, and again, it's okay if you don't have an immediate answer to this, because these things are complicated, and every institutional resource is going to have people who can help you identify the best resources for your needs. But it's really important to keep in mind whether high performance computing or remote computing or any of these solutions work for you. There's no one size fits all solution. If your data and computational needs just aren't large enough to warrant it, it's not worth the time and possibly expense it can take to get into high performance computing. If you're only working with a gigabyte data set and your code works just fine, you may not need some of these solutions, which is why you have to consider where your workflows are the most intensive. Do you need specialized chips like GPUs? Do you have very large data sets you're working with, or that you need to put in long-term storage? If so, you're a candidate for different kinds of remote computing or high performance computing. And you also have to consider, your options based on what you need. Many institutions offer high performance computing clusters, Berkeley and virtually every other UC. There's also national resources, there's cloud companies, and we'll talk about that at the end of the presentation. But for now, just keep these things in mind as we get into some of the more technical details of how you can implement high performance and remote computing. Clint, I'll turn it over to you.
Cool. Thanks, Alex. I'm Clint. I'm a domain consultant for research IT here at Berkeley. I'm also a PhD student in the finance department, and there I frequently use high-performance computing for different aspects of my own research. And today I just wanted to talk to you about some of the high-performance computing basics, give you some conceptual introduction that will hopefully allow you to leverage these tools, and talk about some of the easiest ways where with minimal effort you can get big speed ups using high performance computing, particularly with an emphasis on parallel computing. Next slide, please. And so first, I wanted to talk a little bit about why sort of the focus for high performance computing is on parallel computing. And sort of the very fundamental level, it's summed up by this photo with an ox pulling a cart. And basically, it's easier to find 10 ox that are the regular size than an ox 10 times a regular size ox. And basically, what's happened is that the ability of computers to process data, so CPUs, the central processing units that Alex talked about, were growing in speed up until about 2005. And so if you look at this graph on the right with the blue line leveling off, that's basically showing that our CPUs have not increased much in terms of performance since about 2005. And so the way that we're able to do bigger and bigger computations is not by using a bigger and bigger processor, but by using more and more processors. And so that's what parallel computing enables us to do, is to, rather than try and do one computation faster, break our big computation up into little computations and work on those instead by having different processors work on different tasks at the same time. Next slide. So before I go any further, I wanted to give sort of a very high-level introduction of what a supercomputer is, so you can have this in the back of your mind as we talk about parallel computing and why parallel computing helps you really get the most out of your computing resources. In the very most broad, non-technical terms, a supercomputer is basically a collection of really powerful computers, and generally those are called nodes in a supercomputing context. So that's what I'll mean if I say node, and some really big, really fast hard drives. And what ties these all together is generally some really fast networking capabilities. And so fundamentally, a supercomputer is sort of like your laptop or your desktop perhaps was really powerful and you had a bunch of them and you hooked them all up together. That's sort of how you can begin to imagine what a supercomputer looks like. Next slide, please. So I want to talk a little bit about sort of the very basics of parallel computing, when supercomputers are best, when parallel computing works well, to sort of give you guidance on if your workflow might be a good application for parallel computing. So there's different types of computations. If you want to impress your computer science friends, you can call it Flynn's taxonomy. The fundamentals are that there's, whether you have single command or multiple commands, and a single data or multiple data. So for example, single command, single data is sort of like 2 plus 2. Basically, you can only ask one processor to do 2 plus 2. It's sort of one operation. But now let's say that the single command is 2 plus, so you want to add 2. And you have multiple data, so maybe you want to add 2 to 3, 4, 5. Well, now you can ask one processor to do 2 plus 3. You can ask one processor to do 2 plus 4. And you can ask one processor to do 2 plus 5. Multiple command, multiple data would be like if you want to add 2 and 3 to 4, 5, and 6. And then multiple instruction, single data would be, let's say, you want to run this sort of same set of commands, different sets of commands on one sort of unified data set. So perhaps you have a data set and you want to fit different models, but rather than having all of your processors on your laptop or your desktop being eaten up by running these 10 models, you could use a high-performance computing resource to run them all at the same time. Supercomputers particularly shine in these cases of 2 and 3. So generally, you have a case where you want to run a single command a lot of times on different data sets. And supercomputers are really good because you can split up the sort of running the command on the different data sets and give the command and the chunk of data to the different processors, and it will handle it well. And so that's really how you get big speedups on a supercomputer. I think one really notable exception, if you're thinking about using a supercomputer sort of outside of parallel computing, is if you have a really large data set. So Alex mentioned that one issue you might have is encountering out of memory. And so there's two types of memory on your computer, basically. There's the sort of hard drive where you store your data, and there's the RAM memory, which is very fast, and it's sort of where things you click on your screen are stored. And that is very easy for the processor to access. And so when you're working with data, you want your data to be in your RAM memory, not on your sort of hard drive memory. And so if you have a really large data set, so maybe a 30, 50 gigabyte data set, basically switching to a high performance computing resource, if the node you're working on has a lot of RAM memory, you'll be able to get a good speed up in your computations because the processing unit will be able to access your data much faster than if it had to go back to the hard drive each time. So there's also the case of GPUs, and if you're interested in using GPUs, which I'll touch on later, that would sort of be another reason where you might want to use a high performance computing resource even if you aren't able to use parallel computing. Next slide, please. Thanks. And so this is sort of just a basic visual of what parallel computing looks like to hopefully give you an image in your mind. Basically, if you sort of have a big problem you want to tackle, you could sort of break it up into individual commands and give it to the processor, or you could sort of subdivide it into tasks and then give the subdivisions to the processor. So, for example, maybe you have 100 different starting points that you want to simulate something off of. So you can give 25 starting points to one processor, 25 starting points to another processor, and 25 starting points to another processor. And so that way you can use more than one processor at one time to accomplish your goal and sort of run things in parallel. Running something on a single core is called, you'd sort of say like running in serial, just for context. Next slide. So there's fundamentally two types of parallel computing, and this sort of goes back to that. Basically, the fundamental question is, are you running your computations on one node, or are you using multiple nodes? And so there's shared memory computing, which is all computations are done on the same node. And sort of what the key aspect here is that the objects are able, the processes that you're running and the processors are able to access the same objects in your RAM memory. So it's that very fast memory, and that allows for all the processors to sort of more easily work together and write to the same data set. The sort of alternative is distributed memory, and this allows you to do computation on multiple nodes. However, things get a little bit trickier here because there's not sort of shared memory anymore, and so you have to pay special attention to passing information between nodes when you're using distributed memory computation. One nice thing I'll say is that though distributed memory computation may sound daunting, a lot of cases where you can easily use shared memory computation, you can easily use distributed memory computation. However, generally setting up distributed memory applications is not always easy and might require paying a little extra attention to how you've set up your how you've configured things. So distributed memory is a little bit harder, but particularly if you're using a package that encourages you to use parallel computing, distributed memory can be still easy to use. Next slide. And so, as promised, I also wanted to talk briefly about GPUs. I think this is sort of the other important high-performance computing resource. Basically, a GPU stands for graphics and processor unit, and these are very good at linear computations that are very common in graphics processing. And so, for example, these are very commonly used in machine learning applications and generally accessible at not all, but a large number of high-performance computing resources. For those of you who sort of even go further into your journey with high-performance computing, GPUs are an example of an accelerator node, and the aim is that these types of processing units will be able to provide you a faster calculation speed than a generic CPU, because like I said, the computation speed of a CPU has kind of leveled off. And so by using a GPU, a graphics processing unit, you're able to get big speedups on things like machine learning, which involves a lot of linear computation. And so, for example, a lot of machine learning applications make it very easy to talk about the settings. And with that, next slide. And so I just sort of wanted to close my section with talking about how you can actually leverage parallel computing and high performance computing resources sort of with minimal modifications. So some applications have multi-core versions. For example, Stata is an example that has Stata SE, and then there's Stata MP, which will allow you to use multiple cores. And a lot of high performance computing resources will have if they offer Stata, will offer the multi-core version of Stata. So just by switching your same Stata code to run on a high-performance computing resource with Stata MP, you're able to use parallel computing and potentially get a large speed up in your runtime. Some applications, you just have to change your settings, and so some software packages will allow you to easily change the settings to use more cores. Others, particularly machine learning packages, will have either a different version of the code that runs using graphics processing units, or you just play around with the settings a little bit, and then your machine learning code will be able to use graphics processing units. And you'll get a big speed up using a graphics processing unit because it's specialized in the type of computation that a lot of the machine learning model generating process will rely on. One sort of additional note is that you can sometimes ask the underlying linear algebra software to use more cores. Oftentimes, this will already be configured by an HPC administrator to use parallel processing if relevant. This is mostly applicable to large matrix operations. Lastly, for loops, which is essentially where you iterate over chunks of data. Maps, if you're familiar with what a map, basically a map is you run a function on the different rows in a data set, basically. Or an apply statement is a similar concept. And because these basically have a single command across multiple data, generally for loops and maps and apply statements can be easily parallelized. The one exception is for a for loop. If the sort of current iteration of a for loop depends on the previous calculations in the for loop, then it's not possible to run that in parallel in general, because essentially you can't sort of have one operation running off something that hasn't been calculated yet. However, then the sort of ideal case is to find chunks within the for loop that you can parallelize. And doing parallel for loops is very easy, particularly in MATLAB and Julia. There's the par4 command in MATLAB, and there's @parallel in Julia. And there's many easy options in Python and R. And so, for example, I use Python and I use the IPyParallel, and with a few extra lines of code, I'm very easily able to access a parallel map command. So I just give it a function, I give it my data set, and it will run the function on each sort of chunk of my data set and give me the results in parallel with just a few additional lines of code in Python. And there's similar options available in R, and like I said, MATLAB, Julia, and many other of the common computing languages. And so with that, I will turn it over to Joseph to talk more about virtual machines, containers, in the cloud.
Hey everyone, I'm Joseph. I'm one of the research IT interns, and I'm going to talk a bit about virtual machines, cloud computing, and how they compare to a traditional HPC. Yeah, so what is a virtual machine? It's a virtual computer inside of a physical computer. We call the physical computer a host, and each host computer can support multiple virtual machines. And then while a virtual machine is running on a physical machine, it's completely separate from other virtual machines and processes running on the host computer. Slide, please. So in this picture, there's two virtual machines on the same host. Each virtual machine has its own simulated hardware, which is split from a pool of the physical hardware, and it has its own operating system. Each virtual machine is running its own applications, and the two virtual machines are completely separate from each other, and they're also separate from any other processes running on the real machine. Slide, please. So why would you want to use virtual machines? One of the biggest advantages VMs have is their ability to have an operating system, OS for short, that's different from the host operating system. So this would allow you to run applications that wouldn't natively run on the host operating system inside the virtual machine. So let's say you have like a Linux machine, but you need to run Windows specific software. Instead of purchasing an entirely new Windows computer, you could just configure a Windows VM and then run the software inside the VM. VMs also can have flexible resources. So let's take an example. In a traditional HPC, when you submit a job, you request X number of nodes, and these nodes have some amount of memory. If while you're running the job, you run out of memory, your job's either going to fail or slow down significantly. With a VM, and specifically a VM with in the cloud, it's possible to allocate more resources to the VM while it's running, so your job wouldn't slow or fail. With cloud computing, this process is called bursting, and it's one of the things that makes it so powerful. Similarly, it's fairly simple to add more storage to the VM as long as the host machine has the storage to spare. VMs also offer a way to create a reproducible workflow. So what do I mean by that? Let's say you have software somewhere in your workflow that requires a really specific operating system and loads of supporting libraries to run. If you want others to be able to recreate your workflow, they would have to install the new OS and then install all these new packages and libraries, which could be complicated and take a lot of time. So instead, you could create a VM image, which is just a fully configured VM that has the correct OS and all the necessary softwares and packages installed already. And then you could distribute this image to whoever needs to recreate your workflow. And that'd be much simpler. Slide, please. So now I'm going to move away from VMs for a bit and talk about containers. So this quote comes from one of our previous trainings about containers, and I thought it was a really good definition. So containerization provides lightweight standalone executable packages of software that include everything needed to run an application, which includes code, the runtime, system tools, different libraries and settings. Containers provide a self-isolated file system, and they're similar to virtual machines in some ways, but they're much more lightweight, which I'll get into in the next slide. Like virtual machines, containers are shareable, reproducible, and portable. So what's the difference between a VM and a container? The biggest difference is the operating system. So a VM can have an operating system that's completely different from the host's operating system because it essentially recreates the entire operating system. A container is more tied to the host's operating system because it utilizes some of the functionality of the host's operating system. One of the downsides of the VM recreating the entire operating system is that it takes up a lot more space than a container would, and it also requires more computational power to run than a container does. Both, like I said, both are still shareable and create a way to make a reproducible workflow. So what are some VM example use cases? Like I've said previously, VMs excel when you need a different OS than the host machine. VMs are also really useful when developing software because you can mimic the production environment while developing the software, which can help reduce bugs. Once again, VMs also provide a way to create a reproducible workflow. So what are some challenges to using VMs? For one, they can be expensive to run on a physical machine. So they take up several gigabytes of space, and they also consume a lot of computational resources. So if the host machine doesn't have the resources to run the VM, it can mean the VM will have very unstable performance. And VMs are also less efficient than physical computers because of the virtualization layer, where you're virtualizing the actual hardware. This is mitigated a good bit by many enterprises through really optimized technologies. So what is the cloud and why would you want to use it? Cloud computing is the on-demand availability of computer system resources, especially data storage and computing power, without direct management by the users. And by using VMs, cloud resources offer the ability to create virtual images of specific environments that you can then run on rented scalable machines. So what's the difference between cloud computing and traditional HPC like Savio? A major difference is the virtualization that cloud computing employs. As I've said before, in cloud computing, you use virtual machine that's allocated a certain amount of virtual resources from a pool of resources. In traditional HPC, if you request some number of compute nodes, you're given that number of compute nodes to perform your computations on. If you run out of resources while running your computations, your job's either going to slow down or fail. Because cloud computing uses these virtual machines, more memory or more cores or more storage can be allocated to your virtual machine while your jobs or processes are running. So they may not necessarily slow down or fail like they would in traditional HPC. Another large difference is how you pay for cloud computing versus traditional HPC. With cloud computing, if you don't use it, you don't really pay for it. With traditional HPC services, you typically pay for a specific number of service units, which is just one computational unit, whether you use it or not. Also, not everyone can access HPC systems. Access can be limited to people within certain institutions or people with certain affiliations, while cloud computing is accessible to pretty much anybody with an internet connection and an email address. Both cloud computing and traditional HPC, you can create reproducible and shareable workflows. In cloud computing, this is done through VMs. Traditional HPC, it's done through containers. One of the big downsides of cloud computing is that it can be pretty expensive to get your data in and out of the cloud. It's probably not an issue if you work with smaller amounts of data, but it can become expensive and time consuming if you have larger and larger amounts of data. In the end, there's no definitive better option between cloud computing and traditional HPC. They both have their advantages, disadvantages. It all just depends on what resources you have available to you and what your specific use case is. So virtual machines in the cloud. There are three main cloud computing services. You've probably heard of most of them: Azure by Microsoft, Google Cloud Platform, and Amazon Web Services. There's also Exceed, Jetstream, which is funded by the NSF. They all offer different VM services. They're priced differently and they're tailored to specific needs. A slide, please. So what are some benefits of using virtual machines in the clouds? All of the benefits I've talked about of virtual machines extend to using virtual machines in the clouds. One of the things I haven't really focused on yet is ease of access. Pretty much anybody can access cloud computing, and the different companies that I mentioned a slide ago have all created very easy to use systems, which would make getting into cloud computing simple. VMs also have flexible resources, like I've said. And I think that's it for me. So I'll pass it on over to Leon.
Hi, I'm Leon. I work with Alex and Joseph. And this part of the presentation is essentially can be summed up as the things you should know and ask to get the most out of the resources that are available to you. So next slide, please. Yes. So obviously, the first thing you're going to need to know is what questions you should be asking about your projects, such as the amount of memory that you need, number of cores needed, number of GPUs you might need. Is your code easily parallelizable? Do you need large amounts of data for your job? What workflows and software are you using? And are you working with particularly sensitive data? So in the case of memory, something simply you can do is run your job locally on a smaller subset of the data and extrapolate from that to see how much more memory you're going to need. You can also just analyze your code to see how much data is being loaded in at any given moment. And then you're always going to need and then some for unforeseen things and the code itself. The same general idea comes for the number of CPUs you're going to need. And it also can be understood as the amount of tasks that you want to run at the same time. And then GPUs, come down to if you're going to need something that's graphically intensive or something that takes advantage of vector math. And then, is your code easily parallelizable? That's something Clint went over. And do you need large amount of data? And so that's going to come down to, what storage resources you're going to need, and even possibly if you're going to need to move your compute, to use compute that's close to your data rather than actually move your data, because transferring large amounts of data over the internet isn't actually that easy and quite expensive. And so then what workflow are you going to use? Do you need Linux? Do you need Windows utilities? What domain specific software are you using that's related to your specific research? Then are you working with high security data? You might have data agreements. You might even have like people's social security numbers, and then there are secure clusters for those that require their own procedures. Next slide, please. Here's all the campuses that have a compute facility that is on premises, like Savio at UC Berkeley. So there's usually campus-wide resources, or some of the time at least. And then if there aren't, departments will sometimes also have their own clusters that are specifically set up for their specific domains. So even though we have Savio at Berkeley, we also have a statistics cluster that's specifically for the statistics department, or also the economics department, so that there's software on that students and researchers in those departments actually use. And I believe that UC Davis, the cluster is, different parts of it are sponsored by different departments. So you basically get an allocation there. So it works kind of differently depending on which campus you're on, and so you'll need to find out the specifics there. Next slide, please. Then there's also the Extreme Science and Engineering Discovery Environment, or EXCEED. This was touched upon with Jetstream. It's a virtual organization. It's funded by the NSF, brings together digital resources from around the United States. For example, there's a massive storage farm in Texas for all your data if you need it that way. They also provide consulting resources like we do at Research IT, domain consultants that will also work with you for months to even a year. And then some UC compute facilities also have allocations on it, such as the San Diego Supercomputer Center is part of EXCEED. Next slide, please. Then there's cloud providers, of course, and Joseph touched upon these. Getting these resources is going to be a bit more complicated, mostly because different labs, you need to buy credits for the cloud platforms, and different labs and different campuses and different organizations will have their own relationships. I mean, they do like giving away research grants of credits, but these can be fairly limiting sometimes and won't necessarily be the best. So it can also just cost more to use cloud providers. Next slide, please. And so this is generally how you're going to be accessing these facilities. Again, going to be handled differently by different campuses and departments. We have Savio for every department. Davis has clusters sponsored by departments differing, and they have differing allocation models, which basically just makes talking to consultants a very, very good idea. Usually you'll be able to get allocations through your faculty or principal investigator. Purchases of nodes are also usually available. That's very expensive and not usually necessary to actually use the cluster. And there's also allocations available through grants such as EXCEED, campus clusters, and cloud platforms. Next slide, please. And then to cap it all off, basically there's going to be a compute resources that you can use, most likely even for very little cost. Of course, if it costs a little less, it might not actually be top of mind all the time. Then if you have any other questions, you can reach out to us at these email addresses. Thanks.